Alright, hey everyone, I hope you're well. In this video, I thought I'd go over the calendar question from the 2022 Level 2 Algebra paper. I've seen a bit of talk about it online, and I thought it's actually a really nice question, and it's quite a good introduction to proofs, right? And so I thought we'd go over it today. Not the whole paper, just this part of question. I think it's question 1. So a calendar can be presented in the following way, where each day is given a number from 1 to 365. And so this is the beginning of a calendar for some random year. So Joe draws a 4x4 square on the calendar to check a claim that she heard. The sum of the diagonally opposite corners are always the same, no matter where you make your square. In other words, when you add the numbers in the orange corners, it's the same as when you add the numbers of the blue corners. Joe wonders if this claim will still be true no matter where she starts the square, so she begins an investigation using algebra. So part I. Use algebra to prove that no matter where the 4x4 square is drawn on the calendar, the sum of the orange corners must be the same as the sum of the blue corners. Okay, so how are we going to prove this? Well, first, I guess a bit of background. I was doing some supervision for this exam, and this is what I saw on nearly everyone's diagram. So they had A here, and they put B here, they put C here, and they put D here. And then what they're trying to prove is that A plus D is equal to C plus B. This is really poor, right? How can you prove anything if you've got a whole bunch of different variables, right, that you can't rearrange for because they're not of the same variable, yeah. So actually what you want to do is, if you kind of think about it, right, we're talking about a calendar here, right, where each number is sort of has a relationship with the last, right, in the sense that they're all consecutive numbers, right? So if we use this idea of consecutive numbers, we're going to be able to write a proof for this question. So if I remove all this, and we look at, okay, so what they're saying is they've given us an example here of a 4x4 where they've just put it in some random space here. But we want to show that it holds for anywhere on the calendar, right? So if we chose a 4x4, I don't know, let's say right here, we want to show that it would hold for that too, right? And so in general, we've got A here, right? So because we've got A, are we able to, from here, using consecutive numbers, determine what this corner is, and this corner is? We actually can, right? Because if this is A, then we know that this square here is just shifted 1 to the right of it, right? So that's going to be A plus 1. This square is going to be A plus 2, and therefore the top right-hand corner for this 4x4 square is going to be A plus 3, right? And it doesn't matter where I draw that 4x4, right? It's always going to be A plus 3 in that top corner if it's a 4x4 square, right? So let's say I did it in this bottom corner here. If this value is A, then we would always expect that this value would be 3 values shifted to the right from that, or added 3 onto 49. So what's 49 plus 3? It's 52. So that seems to be okay. I'll just remove that there. Okay, so now here's where we start needing to think a bit more about it, right? So how are we going to go from here to the bottom left-hand corner? Well, essentially, if we just look at what they've drawn here, we can actually just simply count all the way until the bottom left-hand corner, right? So this is A, this is A plus 1, A plus 2, A plus 3, then this is going to be 4, 5, 6, 7, right? 8, 9, 10, 11, 12, 13. 14, 15, 16, 17, 18, 19, 20, 21. So essentially this number here is going to be shifted 21 to the right from A. So this value down the bottom is going to be A plus 21. Now, is this always going to be the case? Well, if I remove this here, essentially, right, if you think about it, this box here is essentially, we're saying the same thing as, look, we want to shift exactly 3 weeks forward from the date, right? Which is always going to be 7 days ahead, right? A week is 7 days, right? So no matter where you start, even if our square, a 4x4 square was starting at 21, we're always going to be wanting to shift some multiple of 7, or shifting some amount of weeks down to the last week, right? So hopefully if I draw a square here, a new square, to try and convince you of that. Look, if I start here and I want to shift exactly 1 week down, that's still going to give me a square which is in the same column, right? And I've shifted it by exactly 1 week, which is 7 days, right? So you can actually count that 1, 2, 3, 4, 5, 6, 7, right? So if we're doing a 4x4 square, this is a 7-day shift, this is a 14-day shift, and therefore this must be a 21-day shift, right? And so that's where I've got a plus 21 from. And then finally, we know that this square here is simply just going to be like the square here, just 3 added on, right? So if I know that this square here is a plus 21, this is 22, 23, and 24. So we know that this square here is a plus 24, right? And so this is specifically for a 4x4 square, right? So now that I've got the values of all the corners, I can simply sum the orange corners and the blue corners and see if they are equal. Okay, so what are we going to do in order to write an actual proof? This is an example of what we call a direct proof. So if this is the first time you're thinking about writing proof, I guess an easy way to start is to think, what do we already know? So what do we know? So what do we know? Well, we know the values of or maybe not even the values, but like the expressions would be a better word, better term for it. The expressions of the left hand, right hand corners, right? So we know all the expressions for all the corners. And so what are we trying to show? So what do we want? So what we want to show essentially is that the sum of the orange, so the sum of the left hand top plus the sum of the right hand bottom is equal to the sum of the right hand top plus the left hand bottom, right? So because we have the expressions of the left hand and the right hand corners, we know all the information to write this out here, right? So let's go ahead and do that. So what's the left hand top? It's a, added with the right hand bottom, which is just the other orange piece, which we know is a plus 24. This is equal to the right hand top, which is a plus 3. That gets added with the left hand bottom, which is a plus 21. So if we simplify this now, this is 2a plus 24 is equal to 2a plus 24. Therefore, the left hand side equals the right hand side as we wanted to show, right? We said that the sums must be the same, right? So this implies 0 equals 0, which is always true, right? Which is always true. So if this equation is always true, that means that the left-hand side must always be equal to the right-hand side, right? So therefore, sum orange corners is equal to the sum of the blue corners as we needed. Okay. Now part 2, Joe wonders about the products of the diagonally opposite corners. Could they be the same? Use algebra to prove that it is actually not possible to draw any 4x4 square for which the products of the diagonally opposite corners are the same. Okay, this actually doesn't require too much work. I'm just going to recopy the square that we've already drawn, and I'm just going to paste it. Oops, paste it here. So I might make it a bit smaller. There we go. So I'm just going to put it, in fact, I might put it up here. Okay, so essentially all we're doing now is we're going to find the products of the orange corners and the blue corners and see if they equal each other, right? If they don't equal each other, then that's a if they don't equal each other, then that means that, well, it's not possible, right? So how are we going to actually write a proof for this? We're going to use a technique that's called proof by contradiction. So how do we use proof by contradiction? We're going to assume that it is possible it is possible that the products of the diagonally opposite corners are the same. When we reach a contradiction, that's going to mean that that statement that we assumed is false and the opposite of that is going to be true. That is, if we get to a contradiction, we're going to be able to say that, well, that must mean that the products of the diagonally opposite corners, the sum of them are not the same, right? Hopefully that makes sense. Okay, so, not the sum of them, sorry. So, the product of the orange corners is not the same as the product of the blue corners, is what we're trying to show. Okay, so how are we going to show this? So let's write our assumption first. So we're going to say, assume that the opposite of what we want to prove is true. So we're going to assume that the products of diagonally opposite corners are the same for a 4x4 square. Okay, so if we assume that this is true, then we can go ahead and actually do that calculation, right? So let's say for the orange corners, so for orange, we're doing a multiplied by a plus 24. And for the blue corners, we are doing a plus 3 multiplied by a plus 21, right? So if we expand these out, this is the same thing as a squared plus 24a, and this here is the same thing as a squared plus 21a plus 3a plus 63, right? So we've assumed that they are the same, right? So that these corners must be exactly equal. So now what we can do is we can write an equation which says that the left-hand side is equal to the right-hand side, or orange is equal to blue. So what we can now say is, well, a squared, in fact, let's write one more step to make it real clear what we're doing. We're going to say orange equals blue via our assumption, right? Therefore, orange, which is a squared plus 24a, is equal to a squared plus 24a plus 63, right? So this is what we've come up with. Now, if we rearrange this equation, the a squareds are going to cancel and the 24a's are going to cancel, and we're going to be left with 0 is equal to 63. This is a contradiction, right? This doesn't make any sense. 0 cannot be equal to 63, right? So we're going to say contradiction. Right, therefore, the opposite, or maybe we say the negation of our assumption is true, right? That is to say, it is impossible for the products of the diagonally opposite corners to be equal. Nice. So this is the last part here. So the question is, will it always be true that the sum of the orange corners must always be the same as the blue corners, regardless of size or shape of the rectangle that Joe draws? Use algebra to support your answer by considering an m by n rectangle drawn on the calendar below, where m and n are whole numbers greater than 1 and m is not equal to n. So we can draw on the calendar, but we have to write a proof. So is this true? Well, honestly, when I first thought about the problem, I wasn't sure. I said it might not be true. But essentially, if you just draw a whole bunch of rectangles of differing values of m by n, so if we draw like a 2 by 2, for example, well, what we can see is that, well, the sums, what's 5 plus 13? 18. 12 plus 6 is 18. So this seems to hold for like a 2 by 2. What if we did a 3 by 2? Does this hold? Well, 5 plus 14 is 19, and 12 plus 7 is 19, so that seems to hold. And then, so even if you keep going, even if you did like a, what is that, 3 by 1, 2, 3, 4, 5, 6, 7. So even if you did a 3 by 7, you would find that 15 plus 59 equals 17 plus 57, right? So intuitively, it seems like this might actually be true. But we can't just give a whole bunch of random examples, right? That's not really how we write proofs, right? We need some concrete algebraic working in order to show this. So how are we going to do this? Well, I'll draw out an extra rectangle, and then I'll go through how we algebraically show the values of each corner, and then we'll write about it. So, oops, if I draw another rectangle like this, duplicate them like so. So these are going to be our corner pieces, right? And we need to find algebraic expressions for all of them, similar to how we did it in part 1, where we had a plus 3, a plus 21, a plus 24. But now this is not for a 4 by 4, this is for an n by n rectangle, right? So what does that mean? It means that we have exactly m squares across and exactly n rows, right? So m columns, n rows. So the first thing we're going to do is we're going to use the same technique as they did by defining that the top left-hand corner must be some variable a. So I think the easiest way is if we just draw a random 3 by 3 in the calendar, this will allow us to generalize to an n by n, right? So if we can get the understanding of a 3 by 3, we can just generalize up to an n by n. So we're saying that the 20 is the value of a in this case, right? So how do I get the value of 22? So essentially we need to shift by 2 from the 20 to get to 22, right? So in this case, we're doing a 3 by 3 where m is 3 and n is 3, right? That makes sense, right? So if this is m across and this is n down, how did I get from 20 to 22? If m is 3, so we got 3 columns, right? This is column 1, this is column 2, this is column 3, and we started with a here. If we add on 3, we're going to get a plus 3, right? But here's the thing, if we did a plus 3, so if we shifted across 3, we'd be shifting 1 too many across, right? Because if a is 20 in this case and we add 3 on, we're going to get 23. But the answer here is actually 22, right? So actually we're just shifting a plus 3 minus 1 across, right, in this case. And the reason for that is because, well, if this was not considered as a, but considered as 0 or something like that, then, and then we moved across, then, yeah, this would actually be, indeed. So this was 0, 1, 2. Oh, sorry, if we consider this to be 1, then this would be 2 and this would be 3. But because we consider this to be like a plus 0, then we can't do that, right? So we actually have to subtract 1 off m in order to reach to the right-hand corner. Okay, so we know that for this rectangle here, the top right-hand corner will be represented by a plus 3 minus 1. So algebraically and in general, for any m by n rectangle, this is the same thing as a plus m minus 1. Right? So essentially all we're doing is we're just shifting across m minus 1 squares to the right. So that's what the top right hand corner. So now we need to look at how we can get the bottom right hand corner. So how do we do this? Well, an easier way to think about it is, if you remember, you can think of this box here as being shifted down some n amount of weeks, right? So if this is week 1, this is like week 2, and this is week 3, right? If this was a 3 by 3 rectangle, right? So if you think about this specific rectangle here, consider this to be row 1, row 2, row 3. Okay. Then, yeah. So if we wanted to get the value here, if we wanted to get the value in the second row, right? So if we don't know how many rows we have, but if we just wanted the value in the second row, how would I work out what this value here would be? Essentially, this is just whatever the value of A is shifted by 7 days, right? Because if you think about it, we're looking at a calendar, and each time we want to go directly down one row, we have to shift by 7 days, because that's like a week, right? 7 days is a week. And so if we want to get directly to the next week, we have to go 7 across, right? So essentially what we're saying is this is A plus 7, right? And we can actually double check this with our example. If I remove all this scribble, this is A plus 1, A plus 2, A plus 3, A plus 4, A plus 5, A plus 6, A plus 7, right? So that looks good. So then if we had another row here, let's say this was a had 4 rows, then this would actually be A plus 7 times 2, or A plus 14, right? Because it's shifted 2 weeks down, right? And so what is the bottom corner always going to be? It's actually going to be A added with some multiple of 7. Now what is that multiple of 7? It's 7 multiplied by exactly n minus 1. Why is it n minus 1? Well, if you look here, think of this 20. This is our row. Okay, actually, it's better to think of this as row 0, right? Because essentially, you can think of 20 as being whatever 20 is added with 7 times 0. You can think of 27 as being 20 plus 7 times 1, which is 27. And this is 20 plus 7 times 2, which is actually 34. But because n is 3, this value is exactly 1 less than 3. So this is always going to be A plus 7 multiplied by n minus 1. Okay, so that's our bottom left-hand corner. And so what's the bottom right-hand corner going to be? It's going to be exactly almost the same as how we worked out the top right-hand corner. We're just going to shift this by exactly m plus 1 over. So this is going to be A plus 7 multiplied by n minus 1 plus m minus 1. And now we can write our direct proof. Okay, so the proof for this is actually quite simple. It's like one line, but we need to actually, I guess, explain how we got all the values in the corners. So let's start off our proof by saying, let A be the value in the top right, maybe top right hand corner. Then the top, sorry, this should be left hand, top left hand corner. Then the top right hand corner is shifted over exactly m minus 1 squares to the right. Okay. Now, how do we get the bottom left-hand corner? So we'll say we can think of the bottom left-hand corner as the number of weeks A has been shifted by. A has been shifted by, right? We'll say as we start at A plus, actually we better not start with that. Let's remove that for a second. And let's just say instead, well, that is the first column can be thought of as A shifted by some multiple of 7, right? We're saying that this is A plus 7 multiplied by some multiple, and that multiple is actually n minus 1, right? So we'll say n minus 1 comes from the fact that we start at row 0, right? This is like I.E. Top left hand corner is a plus 7 0. So sorry, we don't actually start at row 0, we start at row 1. Cool. So if we start at row 1, then this row here must therefore take the value of n minus 1, right? Otherwise we'll be 1 too many over, or 1 rows too many down, right? And then we say, what do we say? We say the bottom right hand corner is the bottom left hand corner shifted by exactly n minus 1 squares to the right. Okay, because it's exactly the same as what we did here. Okay, so we don't really need to re-explain that. So now let's actually do the proof, which is a one-liner, I think. So what's the opposite squares here? We're saying that a added with a plus 7 n minus 1 added with m minus 1 is equal to the other corners, which is a plus m minus 1 added with 7 multiplied by n minus 1 plus a. Okay, and if we actually just double check this, we've got two a's, we've got a 7n minus 1, a 7n minus 1, and then an m minus 1, and an m minus 1. Okay, so what does that mean? Well, this implies 0 equals 0, which is a tautology, which means that this is always true as required. Okay, and then that's the end of our proof. Okay, so yeah, I think that's it for that part of the question. It definitely is a bit of a tricky one for an exam, right? But yeah, I think it's a really nice proof flavored question. We don't usually see that from NCEA, so it's probably a bit of a shock, but if you want to go on to do any maths at university, this is the kind of steps of thinking that you need to take, right? So I guess just that thing that I saw where everyone was writing A, B, C, and D, this is not how we can write proofs, because like we don't have any way of making comparisons if everything is defined by some different variable. Anyway, I hope your exam period is going well, and I'll see you guys in the next video. Cheers.